So we've now started to see some interesting examples of recursion. In the case of Towers of Hanoi, we saw an example where the recursive call might involve multiple subproblems, in that case too. We also will see examples of recursion where it may have multiple base cases. And let's look at another classic example, the Fibonacci numbers. The history of this is, several centuries ago, Leonardo of Pisa, also known as Fibonacci, wanted to model how quickly rabbits breed. And he built a model that's not completely realistic, but still gives you an interesting process. And he described it as follows. He took a newborn, or he wanted to take rather, a newborn pair of rabbits, one male and one female, and put them in a pen. He assumed that rabbits mate at age of 1 month, and that the gestation period for a rabbit is also a month. So after 1 month, rabbits can mate. A month later, a female will produce offspring. And in particular, he assumed that the females will always produce a new pair, one male and one female, every month from the second month on. And finally, he assumed that rabbits don't die. It is not true, but it's an interesting way to try and deal with it. And the question was, how many female rabbits are there at the end of 1 year, 2 years, however many years? So, that was the model. Here's how we can actually think about it computationally. We want to know the number of females. So, at the end of 1 month, let's call it 0, we've got 1 female. That's what we started with. After the second month, there's still 1 female, but she's now pregnant. And at the third month, she's going to deliver. So in fact, not only is there now that female, but there's a second female. 1 pregnant, 1 not. And in general, we can figure out the formulation, the sort of recursive expression, if you like. Because in general, every female alive at month n minus 2 is going to produce a female at month n. It takes 2 months for that to happen. Those new females that are generated at month n can be added to those that were alive the previous month, because those are the new females. So the total number of females at month n is the number that were alive at month n minus 2, because each one of them has produced a new offspring, plus all the ones that were alive at month n minus 1. And so you can see at month 0 there will be 1, at month 1 there will be 1, at month 2 there will be 2, and at month 3 there will be 3. And now you can see we're just adding to create the next one. At month 4 there will be 5, at month 5 there will be 8, and 13, and so on. Okay, we don't really care whether this is a good model for rabbits, although you can see why Australia may be suffering the problems it does when 24 rabbits were introduced into their ecosystem. But let's think about just writing code to capture it. Description is nice and easy. And notice here, Fibonacci has 2 base cases. Base case for the 0th month, base case for the 1st month. That base case in both instances is 1. And then the recursive case is what we just described. Okay, and the code, nice and simple. I'm going to add one new thing here, which is this assert statement right here. So let me spend a second on that. Here's my definition for Fibonacci. I've got a specification. It says assume that x is an integer and it's greater than or equal to 0. If that's the case, I'm going to return the Fibonacci number of x. Assert is something that basically takes an expression, which is a Boolean. And in this case, it's an expression that has 2 sub-expressions, both of which are Booleans. And what assert does is it checks to see, is that statement true? So here what you see we're doing is we're saying, given x, let's make sure that it is in fact an int by checking its type. And let's make sure that it satisfies the condition of being greater than or equal to 0. And if both of those are true, then the body of the procedure will be evaluated. But if either of them is not, if the overall expression for the assert is false, it's going to stop and return an error. Inside of fib, it's exactly what we'd expect. I've got 2 base cases. I happen to be checking them with just 1 Boolean combination. But 2 base cases and a value to return, and otherwise I'm returning, just like in Towers, a recursive call done twice, I'm returning the sum of fib of x minus 1 and fib of x minus 2. Okay, let's try running it. So I'm going to go over to idle, and I have my version of fib. And let's check. Let's check the base cases. Fib of 0 should be 1. It is. Fib of 1 should be 1. And then what did we also know? Well, we said that fib of 2 ought to be the sum of those 2, and it is. Fib of 3 ought to be the sum of the previous 2, and it is. Fib of 4 ought to be the sum of the previous 2, and it is. And you can see it's doing pretty well. And so, how many at month 12? 233. Gets bad fairly quickly. Just to give you an example of that, at 13, it jumps up. And if I go to something like, say, fib of 15 or fib of 16, it's climbing pretty quickly. But there we are. We've got a way of computing Fibonacci. Great.